other purposes as well, I was told. Just wanted to remind everyone that after the lunch today, we will go out. The theoretical prediction is the weather would be nice, and we will be able to take a photo, a group photo. So everyone is invited. And today we have 4 presentations following the excellent ITC colloquium that Brant Robertson gave, showing us that how to make a video game of galactic outflows with GPUs. We'll start with Michelle Ntmpaka. Did I say it right? Oh, Ntmpaka? Ntmpaka. Who is at the ITC, but also at the Harvard Data Science Initiative. And she will tell us about cluster cosmology with the velocity distribution, galaxy cluster mass estimates with deep convolutional neural networks. And then we'll hear from the colloquium speaker today, the CFA colloquium speaker, Renu Malhotra, sitting over there, who is visiting us from the University of Arizona. And she will tell us about the mid-plane of the asteroid belt. Then we'll hear again from Brant Robertson, that many of you remember from the time he was a student here a long time ago. And by now he had a very successful career. Currently he is at the University of California, Santa Cruz. And he will tell us about dense regions in supersonic isothermal turbulence. And finally we'll hear from Jerome Quintin, who is visiting us from McGill. Even though he's last in the list, he will speak about the earliest moments in the universe. He will talk about the black hole formation in a contracting universe. So that means the phase before the Big Bang. Michelle.
All right, thanks, Avi. So my name is Michelle Ntmpaka. I am a postdoc with the Data Science Initiative, but I sit here in the ITC. And I'm really interested in questions in cosmology and machine learning tools that can be used to answer those questions. And so today I want to talk to you about galaxy cluster mass estimates using deep convolutional neural networks. This is a composite image of the Virgo cluster. So what you're seeing here is both galaxies as viewed in visible light, as well as a Chandra X-ray observation of the hot intercluster medium. This allows me to sneak in a little bit of background information. So here's what we're after. Clusters are massive, they're rare, and they're sensitive to the underlying cosmological model. So if we can count them up as a function of their mass and their redshift, we can use that to constrain cosmological models. But the trick is clusters are shy about their mass. And so one of the pieces that we need for this puzzle is low scatter mass proxies. And today I'm going to be looking at a low scatter mass proxy that uses just the Chandra portion, just a Chandra-like observation of a galaxy cluster. So I'm using simulated Chandra images. These are built from the illustrious TNG simulation. I have 329 clusters with an M500 going down to about 10 to the 13.5 or 10 to the 13.6. I've augmented this sample with many different views of each cluster. And my observations are Chandra-like, but I've moved into a lower resolution. So I've moved into a space where I have lower spatial resolution and also lower, actually no, energy resolution. There are a number of different ways that you can take an X-ray observation and turn that into a mass, and I'm going to talk about one. So this is a plot from Mon 2007, and what I'm showing here is along the x-axis mass, on the y-axis luminosity. It scales as a power law with some scatter. But the plot thickens. Luminosity kind of near the cores, the inner about 15% of R500 has a lot of scatter with mass. There are morphological signals that also increase scatter in mass. And cluster dynamical state can affect selection probability. Okay. What do you need to take away from this? There is a method that scales an observable with mass, but there are a number of complications that can perhaps add information. And this is really the home turf of machine learning, right? We've got some scaling relationship that we pretty much understand, and some added complications that we may be able to use to squeeze more information out of the data. So the tool that I'm using is a deep convolutional neural network. I honestly could probably spend a semester on this slide alone, but I will hit just the highlights. A deep convolutional neural network starts with an input image with the goal of predicting a mass at the output neuron. And basically what it does is it learns convolutional filters, weights, and biases to predict that answer with a low mean squared error. Now there's one part of my implementation that is really important, and that is that I'm using a 10-fold cross-validation, and that one gets its own slide because I think it's worth shedding a little bit more light on what that means. So I take my data set, I divide it into 10 folds, just chunks of data, and I'm going to call folds. 8 of those folds will be my training set. Those are the ones that the convolutional neural network will see. One of the folds will be my validation set. I'll use that to define stopping criteria to decide when my training is good enough. And I will present results for a final fold, the prediction fold, or the test set, which the CNN has never seen before. Okay, what do they look like? So what I'm showing here is a scatter plot of mass, true mass along the x-axis, and predicted mass on the y. And you probably notice a couple things. The first thing you probably notice is these vertical smears of data. So I mentioned earlier that I'm augmenting the data, so what you're seeing is many different clusters, different views of those many different clusters. Second thing you probably notice is that this tool has a tendency to over-predict at the low mass end and under-predict at the high mass end. So this comes about because machine learning tends to be not real good at extrapolation, tends to pull toward the mean near the edges. So in practice, if you were going to apply this to an observed cluster catalog, what you would want to do is make sure that your training catalog spanned a much larger range in mass than you believed held your test catalog. So now you kind of want to just focus on the middle. The third thing you probably notice is that there's a small tendency to underpredict. This is really driven by the fact that the low mass end is well sampled. So I have a lot more clusters at the low mass end. Very massive clusters are quite rare. There's 2 ways we could deal with that. One of them is to get a bigger training sample. Now, illustrious TNG is one of the biggest, so that just requires some patience, I think, on my part. Another is to assume that this bias is something that you would need to calibrate against observations. So you would take some sample of weak lensing masses to calibrate that bias. Here's the same information shown in a different way. So what I'm showing here is a PDF of errors. The blue is my method. The red is the reported errors for methods that use resolution, lowish resolution data like the stuff that I'm using, but uses no spatial or spectral information from that data, just a global signal. That gives kind of in the 15 to 18% error range. Really good cluster observations that are well resolved spatially and well resolved spectrally give something more in the 5 to 7%. So I've shown here that there is more information in these lowish resolution observations that we're just not using. All right, convolutional neural nets are really hard to interpret. And so to try to understand what this tool is doing, to not just use it as a black box, I turned to Google Deep Dream for some inspiration. Google Deep Dream takes a trained convolutional neural net, and it asks the question, how would I have to change the input image to get a different answer for the output image? How would I have to change this picture of an astronaut so that my CNN no longer sees it as an astronaut but sees it as something else? And here's one that I ran. All right, so you can see, right, they're creepy. I recommend not doing a Google image search for Deep Dream because they're really disturbing. This is one of the less disturbing ones. So you can see it picked up on the hoses on Buzz Aldrin's chest, it turned that into a dog. It picked up on the horizon and made some city scene, and there's like a creepy sort of duck thing in the lower left-hand corner. All right, so I'm not going to be adding ducks to my clusters. I ask the question, how would I have to perturb my input image to change the mass of my cluster? Here's the result. What I'm showing here is along the x-axis radius, on the y-axis a fractional change in photons. Where does the CNN tend to add the photons to make a cluster more massive? And the answer is really interesting. It ignores the center. We saw earlier that there's a really high scatter in the center of a cluster, with the center of the cluster and the mass. People excise those cores. They just cut them out because they introduce a lot of scatter. My CNN, without me ever telling it to do so, learned to excise cores, with the exception of one cluster. This one, it did not excise the core. Well, I thought so at first. And when I actually dug to see what was going on with this cluster, I found something interesting. And that is that off-center from the cluster, off from the center of the cluster, there was a really bright spot. And that's where the CNN decided to ignore the region. So when I asked it to change the mass of that cluster, it honed in on some off-center bright spot. This is really useful information because now we have a bit of an understanding for what this neural net is looking at when it decides a cluster mass and what some of the failure modes might be, where we might need to be a little bit careful in applying to observation. So I will conclude here by telling you the things that I've already told you, and that is that deep CNNs are a really nice tool because they require very little processing of the input image. And they learn features to regress, in my case, or classify images. And on my augmented sample of 329 Mach clusters, they predict masses with an error of about 5% intrinsic scatter, though with a negative bias. And the tool learned to excise cores, which is really interesting. It ignored the portion of the observation that is known to contain significant scatter with mass. And the tool can be interpreted using a deep dream-inspired method to change cluster masses and see what happens. Thanks. Yes? Yeah, so CNNs actually have been used to classify galaxies. They were used to identify weak lensing arcs in large samples of data in actually a competition. And this tool actually went head-to-head against humans. There was one group that just chose to have grad students stay up all night and do the work. And the CNN did better than the tired grad students. Yeah, yeah. Yeah, I would say proceed with caution, and I'll tell an anecdote that I cannot verify if it's true or not, but here's the way the story goes. The US government, maybe in the 70s or 80s, wanted to take a catalog of photos and identify, is there a tank in this picture or not? And they trained a neural network to do this task. But all of the pictures with tanks in them were taken on sunny days, and all of the pictures with no tanks in them were taken on cloudy days. And so instead of identifying the thing that they thought they were identifying, they were picking up on the weather. So I'm going to say that you want to make sure that your training sample is representative of the thing that you're testing on in order to feel comfortable and confident using a tool like this.
Yeah, I have a comment about this systematic.
Mm-hmm.
I have the impression that this is conceptually similar to the fact that when you're feeding a multidimensional scattered data set, your solution, and if you're doing it just like in chi-square sense, your solution will be based to the origin of the parameter space, which is deal with the data better. So I would recommend you to change your training set to uniformly sample the mass range.
So my training set actually does uniformly sample the mass range. What I've done is I've taken my clusters, arranged them by mass, and then I do the thing that you do in elementary school. You go to fold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. So they are uniformly sampled with mass as much as is possible. What's that? So your question may have been, what about creating a sample with a flat mass function?
Yes.
And I am waiting for a big enough simulation to be able to do that. So if any of you have HydroSim codes and lots of computer time, we should talk after. Yeah, because I would love something like that for training this.
And you mentioned that the reason that Michelle mentioned an example from elementary school and that she's so clear in her presentation is that she used to be everything you explained was so clearly explained.
Thank you. Yeah, absolutely.
Oh, here it is. Just gotta wait 1 minute. I'm Renu Malhotra. I'm from the University of Arizona. And I'm going to give you 10 minutes of this brief summary of this paper that we published with this graduate student, Saverio. We asked this, what you might think is a boring question. What's the midplane of the asteroid belt? You probably learned in grade school that all the planets orbit in the same plane. Did anybody learn differently in grade school? Okay. Of course, the planets don't orbit exactly in the same plane. They're a little bit off from each other. The asteroids' orbit planes are even more widely dispersed. They span many, many tens of degrees relative to the planes of the planes of the planets. Why is it interesting? Why is this question interesting? There are a number of reasons why this question is interesting. That unseen planets, for example, will affect the asteroid's midplane. External perturbations will affect the midplane. So the midplane of small bodies in the solar system is actually an excellent probe for unseen massive bodies that might exist elsewhere, or things that have happened to the solar system in the relatively recent past. The other motivation here was that the last measurement was published decades ago, and since that time, many more asteroids have been discovered, so we can do a better, a more precise estimate, observational estimate of the asteroid belt midplane. Now, before we start, we want to know, what do we expect it to be? Okay, so it's going to be, you might expect that it's close to the planes of the planets, and that's true. But to do a precise measurement, there's a theory called the Laplace-Lagrange secular perturbation theory that identifies the expected midplane for a small sample of asteroids that have a small dispersion in their mean distance from the sun. And what you're seeing here is, so the inclination of the orbital plane of any asteroid can be decomposed into a piece that's forced by the planets and a random part. And the random part is, what's called the free inclination. The free inclination is random for the sample. The forced is the part that the planets enforce. And this is what we expect. It's not a flat plane. Okay, it's somewhat warped. There's actually a very substantial warp near the inner edge of the asteroid belt, as you can see here, and that's induced by what's called a secular resonance. where one of the precession frequencies of the nodal precession frequencies of the planets latches on to an asteroid's free precession frequency. And asymptotically, as you go out in the asteroid belt, the plane approaches the orbital plane of Jupiter. So the theoretically expected midplane is not exactly flat, so that makes it a more interesting problem. And so it has this warp, and so we can test this secular theory with a large observational sample of asteroids, which is a rare test for secular perturbation theories in astronomy. So the first step then to do this is to define a sample, an observational sample. We have about 500,000 asteroids now discovered, most of them in the last 10 years. And we can't use the entire sample. We limit it to the observationally complete sample, and there's another little complication that many asteroids are actually members of what are collisional fragments, so asteroid families in the asteroid belt. And so if we pare those down, the usable sample is about 90,000. That's still a big sample, okay, huge sample compared to what has been done before. The last time this was done, the total number of asteroids was around 2,000. Okay. So how do we measure this? We take the unit vector normal to the orbit plane of each asteroid in the sample, and we take the average. So it's a very simple problem that way. We find the average plane of all the orbital planes of the asteroids. As I said, they're widely dispersed. One of the big challenges then is to estimate what is the uncertainty. How well are we measuring this? We do this with bootstrapping with replacement. It's a standard technique in large samples in astronomy. So what I'm going to show you is results like these figures where we have this component, sin I, inclination, and the rotation angle of the plane, the nodal angle, and sin I cosine omega here, and sin I sine omega up on the vertical axis. And this is times 10 to the 3. Okay, so basically here's the first thing I'm going to show you is what is the average plane of the entire asteroid belt. And this is our measurement, that cross there, and this is the dispersion, our uncertainty, our measurement uncertainty, which is on the order of 1/10 of a degree, 3 sigma estimate. Okay, so that's a pretty good high precision measurement now of the asteroid belt midplane. To make sense of this, let's compare it to what has been measured before. This was about 100 years ago. Plummer measured the midplane of the asteroids at about 800 asteroids at the time. So this is quite distinct now from Plummer's measurement. Something like 2 decades ago, there was another measurement there in 1991. Our measurement is distinct from that. It's very distinct from Jupiter's orbital pole and the average plane of the total angular momentum of the solar system. So it's it's probably an unprecedented measurement of any midplane of a small population in the solar system. Okay, so this is the entire asteroid belt. We wanted to test the secular perturbation theory. To do that, we slice up the asteroid belt into little bins in semi-major axis, mean distance from the sun, and ask what is the midplane as you go out from the inside to the outside of the asteroid belt. And so these are pictures. Each panel here is this 1/10 of an AU slice. The blue points are the the predictions of this theory, and the gray dots and the crosses are the measurements. And in most of these, across the entire asteroid, so we have 12 bins, so the asteroid belt is a little over in one astronomical unit across. We have a dozen bins here, and in most of these bins, we see that the measurements and the theory are pretty close to each other, within 3 sigma. There are 2 bins where they're not. One is at the inner edge of the asteroid belt, out there, and one is here near the outer edge of the asteroid belt. And this is not because the sample sizes are smaller or different. Actually, in the inner edge, the sample size is somewhat smaller, but that's also where we have this big predicted warp. Okay, so it's possible that our theory, the Laplace-Lagrange secular theory, is deficient in some way. Here, there's an orbital resonance with Jupiter, which might be affecting the theoretical prediction also. So these are 2 bins where the predictions are different by more than 3 sigma, quite dramatically actually for that inner part. The other thing is that there's a systematic discrepancy. So I've shown this result a couple of times now, and several people have noticed this, that the offset, if you look at the prediction versus the measurement is always sort of southeast of the prediction. And so there's this hint of a systematic offset of the measurement from the prediction. And these are my conclusions. So the asteroid belt's midplane has been measured to this 1/10 of a degree precision. It's distinctly different from Jupiter's orbit plane and the solar system's invariable plane. A slightly warped midplane is predicted. The measured midplane is more or less consistent, but we find these deviations. And in the future, what I'd like to do is to understand better the limits of the theory, as well as the limits of how well can we measure planes in planetary systems. A practical application of this is that an accurate measurement of the midplane offers a novel method to identify those free inclinations, the distribution of the free inclinations of asteroids, and that is used in identifying asteroid collision families. It's part of the way we identify the fragments that are produced during collisions amongst asteroids. And I thank you for your attention.
Renu, did you find anything unusual in terms of the assumptions that go into the branch? You show this random vector. Can you test those assumptions in any way?
So it's a very simple theory in some sense. It's a linearized version of the solar system where you spread the mass of each planet in an elliptical ring and ask how that mass affects each other. The planets affect each other, and they affect any tracer particles. So we can test that. The systematic discrepancy that we find might have something to do with the deficiency in the linearized theory. Maybe there are nonlinear effects that affect the midplane. It's actually a little hard to wrap your mind around that. Why would the midplane is not going to be very different from the plane of the planets? So one shouldn't need any nonlinearities. Okay? It would be hard to imagine that any nonlinearities will produce this large discrepancy. So I think that's not where the answer is going to lie. The answer is going to lie probably in what the asteroids are actually doing. One intriguing possibility is that a recent perturbation to the solar system is relaxing, and that's what we're seeing in the systematic variation. So, future work. Yeah. Roseanne?
Well, this was kind of related because I was wondering, you mentioned these intriguing possibilities at the beginning of possibly discovering another planet or finding a perturber or finding evidence of a perturber, which you sort of addressed the latter one now. I'm wondering how different would your results have to have been from the ones that you showed in order for you to make a statement that points to one of these effects in a very definite way?
Yeah, so this is an inverse problem. There are inverse problems that are really hard to solve. There's a huge parameter space for solutions. What I can tell you, my present state of understanding with this is that something I'm going to talk about this afternoon is planet X, and all the planet X's that are being considered are far too weak to produce the systematic, any of these discrepancies. So this is a huge discrepancy that we are seeing. It doesn't look like that, naively, but none of the planets that we are talking about, this planet X out beyond Neptune, is able to do anything as big as what we see here.
And also not an interstellar intruder, right? Because we had the Oumuamua last year discovered, but it would have very little effect.
Oumuamua is a tracer particle. Yes.
This 0.1 degree,
Yes.
it looked like your measurement is a lot more accurate than that, because you were showing a scale that was 10 to the 3 expanded, right?
Yeah, that was radians, effectively.
It was radians, not degrees.
Sine inclination.
Okay, so
Yeah.
that's where I'm missing the factor of 10 to the 2. Okay.
Okay.
Would you have expected any residual effects of early solar system planet migration to be evident? in the asteroid belt data that you're looking at, or would that have long been relaxed out?
So in the mid-plane, the timescales for relaxing, if you perturb the asteroid belt today, the timescale for relaxation is on the order of not much longer than 1 million years. If you're thinking about planet migration 4 billion years ago, that's unlikely to have any, that would have relaxed away long ago in terms of the mid-plane. There are other effects of planet migration in the asteroid belt, and we can talk offline about that. It's in the entire distribution of asteroids and semi-major axes and so on. There are residual effects of planet migration in the asteroid belt, but not in the mid-plane.
Do you see any evidence?
Yes, we do. Yes. Be happy to tell you about it.
How close should the intruder be if it's solar mass?
You mean a passing star? How close would it have to be? To make this kind of, I don't know the answer to that yet. Yeah. Certainly, I better not say anything yet.
Because that statistic we can estimate.
Pardon me?
We can estimate how frequently stars are passing by. Obviously, the galaxy.
Really, you can estimate? I'd be happy to get your answers on that. I don't know how to estimate that. I think our census of nearby stars is really incomplete.
Well, let's talk about it after.
Okay.
Let's take the round again.
Yeah, the HDMI. Got it. Can you hear me okay? Got it. Thank you. Thanks for the opportunity to give yet another talk here. My name is Brant Robertson, and I am an associate professor at UC Santa Cruz. Today I'm going to talk about dense regions in supersonic isothermal turbulence. Here I've just performed a couple of supersonic turbulence simulations. I used the code Athena to do this, written by Jim Stone and his collaborators. This is a Mach 5 supersonic isothermal turbulence simulation. And in the simulation, Athena is a grid code, but I've implemented a tracer particle scheme so I can use some of the techniques and tricks that I was used to in dealing with particle data on the grid code data. So what am I interested in? Well, I'm interested in the dense regions of supersonic isothermal turbulence. So turbulence, we know, is a reasonable model. It's the best model that we have for star-forming cold clouds in the Milky Way. The typical RMS velocities in those clouds greatly exceed the thermal random motions in those clouds. So we believe that the clouds themselves are supersonically turbulent. And the cooling processes are quick enough that you can treat the gas as roughly isothermal even when shocks develop in the fluid. Okay, but turbulence is notoriously complicated. So here I'm going to fly through a three-dimensional rendering of the 1024 cube simulation. Here I'm showing iso density contours. Red contours are lower density, blue contours are higher density. It's the logarithmic density. We'll fly around a little bit here. So there's a couple of things you'll notice. So I've picked out some isodensity contours. There are large holes apparent in this fluid, and that's because the density distribution of turbulence is quite broad. It has very large, the volume filling density is below the mean density, but the highest density regions extend to many times the mean density. And the structures themselves have different characters. So actually, if you look at the densest regions, their velocity fields are different than the low density regions. And there's been obviously a lot of work done on this. Many people are familiar with Kolmogorov turbulence. This is non-compressive turbulence, isothermal turbulence. But once you have shocks develop, then the turbulence is no longer Kolmogorov. It has a density, velocity power spectrum that is steeper than Kolmogorov is. And also you get these compressively formed shocks that develop. And you might wonder, well, what is the structure of the shocks? Those shocks, the dense regions that you're seeing, these are the initial conditions for star formation on large scale. Okay, if you think about where in the turbulence will be most likely to form a star. Going with the dense regions is the first place to go. And most of our understanding of turbulence comes not from looking at dense regions or looking at structures individually in turbulence. They typically come from modeling the large-scale properties or the statistical properties of the turbulence. Things like the density PDF, the probability distribution function of isothermal supersonic turbulence is close to isothermal, but it depends, or close to log normal, but it depends on the way in which the turbulent driving field is applied. So there's some information there, and there's been a lot of work on that. The velocity power spectrum, as I said before, is steeper than Kolmogorov, steeper than minus 5/3. And as you increase the Mach number of the turbulence, the power spectrum becomes steeper and steeper, closer to Berger's turbulence. And there's been a huge amount of work on this, and so I just threw up a bunch of names. But given the time, I can't go into much detail about any of this work. So you might ask, well, what are you going to tell us then? Well, I'm going to focus on what is the physical structure of these dense regions, and this is something that really hadn't been discussed in the literature before we got there, at least in astrophysical context. Okay, so you may all have, I'm sure you've all learned about isothermal shocks before, and this is the general picture. You have some fluid that's moving from left to right. It's encountering some pre-shock material, and we can pick a reference frame where this stuff is at rest with compared to this fluid. Fluid has a velocity of a Mach number times the sound speed, and there's different densities ahead of and behind the shock. In the kind of classical infinite shock picture, the density jump across the shock is Mach squared. Okay, but as you may have noticed from these simulations, the shocks themselves, they look pretty thin. Okay, so clearly this infinite uniform post-shock structure is not applicable to these complex models, and the reason is that the shocks themselves are not infinite; they're finite in spatial extent, and so they have some structure, and you might wonder, well, what is that structure? What happens behind the shock? And that's what we're interested in knowing. Okay, so let me give you a model for what might be happening. Imagine a finite shock. This is the shock here. You can think about the shock as kind of a snowplow or a bulldozer. Snowplow is evocative, but let me avoid that for the time being. A bulldozer, it's running into some wind. It feels a wind. That wind has a density, uniform density, and a uniform relative velocity. And so it feels a ram pressure associated with this. So there's a force per unit area applied to the face of this shock. And you can think of this as a deceleration acting on the shock. The shock has some surface density. It's encountering a pressure. Take the ratio of the two. That's a deceleration. Okay, so you can imagine the shock is being decelerated at some rate. So you have an isothermal gas that's encountering an acceleration field. This may be familiar to many of us as the Earth's atmosphere, at least approximately so. You have an isothermal gas, a rough constant acceleration near the Earth's surface. You would expect a density distribution that's falling exponentially behind the shock. Okay, or in this atmosphere, and now behind the shock. So what we can do is we can just calculate what is the pressure gradient behind the shock that would supply enough counteracting force to balance out this incoming deceleration from the ram pressure. Okay, and when you do that, you can work out what the density distribution behind the shock should be. And so that's what we did. So we went to our simulation, and we used the simulation to identify tracer particles into groups. So I just used some FOF scheme to identify groups. And then what we did is we oriented ourselves into the frame of the shock. So the shocks are kind of sheet-like. That's an interesting feature of them. They look like ribbons in projection or filaments in projection, but that's basically just because I'm projecting through a structure that is thin and curved. And so it looks ribbon-like, but actually they're sheet-like. And if you rotate, as you saw in the initial movie, if you rotate through the volume, you can see that sheet-like surface appearing again and again. So I can measure the mass distribution in the azimuthal direction away from the center of the shock, the mass center of the shock, and then measure what the density profile behind the shock is. Now, in order to do this, you have to have some interpolative scheme to figure out, once I've oriented myself into the shocks frame, along what direction am I measuring the density and velocity properties of the shock. And so, I had to come up with a variety of interpolation schemes, and it turns out that this answer is fairly robust to that. And so I took all of the shocks in the simulation, so I identified all of the regions that were of relatively high density in the simulation. I oriented the faces of those shocks, and then measured skewers through the shocks and measured the interpolated density profile from the grid calculated densities at each one of these positions. I measured an exponential scale length for those regions, and then I rescaled everything so they could be on the same graph. And what you see here, these lines are each individual shock, and then I've just taken the average shock profile, that's in blue. These are different interpolation schemes, blue and red here. And then I'm showing exponential with a dashed line. So out to several scale lengths, this density distribution is indeed exponential. And the reason why it diverges from exponential out here has to do with the other structure around the material. Eventually, it's not isolated anymore. You're running into the background. And how far out that occurs depends on the density of the shock that you're looking at, because the densest shocks are very, very thin. So the number of exponential scale lengths that you can trace them out is somewhat limited before you start seeing the environment around it. And what's interesting is then you can think about turbulence not just as some fluid on a grid that I can measure some power spectrum for, but actually individual objects, shocks. And you can recover the density PDF of the turbulence as a summation of the density PDFs of the individual shocks. It's easiest to do that in a cumulative sense, so that's what I've drawn here. This is the cumulative distribution function of the simulation and the shocks. And you can see that you can recover the dense part of the CDF just from summing up the shocks. It's hard to say when the shock ends, and so that there's some overcounting, and that explains this mild difference. Okay, so, I'm almost done. So you might say, well, Brant, I don't believe you. I believe students that were here more recently than you, much more than I believe you. So luckily, a very smart group of people, a postdoc here, formerly Blakesley Burkhart and Philip Most, they made the same measurement in some simulations that they did completely independently, and they verified this picture. This is a MHD simulation, but using an entirely different simulation method, and they come up with something that is quite exponential. This is a weakly magnetized shock, and they were following some suggestions in our paper that this picture of an exponential shock may be changed if the pressure support inside of the shock varied because of magnetic field. They looked into that. Okay, so it's been independently verified. Great. So then I'll just throw up my summary since I've run out of time. I'll answer any questions you have. Thank you. Yeah.
Does it match as well?
Yeah, roughly, although in some cases it's limited by resolution. So we've done higher resolution simulations and we seem to verify that it follows, but there is a good deal of scatter there, I agree. One thing that you can do to independently verify this is you can calculate how the scale length changes with time, which we did in the paper. So if you imagine that the shock is being decelerated, the Mach number of the shock declines over time, and that means the density profile behind the shock has to adjust to maintain this rough hydrostatic balance. And the rate at which those shocks spread seems to agree with the prediction that you would make just from a simple model for how the shocks should travel through this fluid. Yeah.
On the scale height itself again, are you using a single scale height for all of your shocks, or you're fitting H for each shock?
Each. It has to be, because the scale height of each shock depends on the Mach number, because the gradient of the pressure is what supplies the rho g counterbalancing. And so you expect for denser shocks that they're thinner, and that's definitely something that we see. So if you change the density of the shock, lower density shocks have broader density distributions. And then if you trace individual shocks, they start with very, very thin scale heights, and then they spread over time. And like I said, in response to Avi's question, that time dependence seems to be in line with what you would predict from a simple model.
So the plot was actually showing all the shocks, but each
Well,
individually.
but I picked out, that's right, that's right, and rescaled based on the scale length that I fit to them. And you can see, so one thing that I would mention, and actually something that's superior that Philip and Blakesley did, is they're using a repo, which you can actually track the shock face directly. So they don't have this issue of having to guess at what direction the shock is facing inside of the simulation volume. So you can tell that they have a much cleaner signal close to the peak than I do. I think it's just basically the messiness with interpolating near the peak of a very, very fine feature in the Cartesian grid.
We should comment, of course, that the regular shocks that we see in the laboratory or here are very sharp. The width of all the mean time.
Yes.
It's completely different physics.
Yeah, that's right. So there's some numerical diffusion which broadens the front of the shock. I'm looking behind the shock here. I mean, they are relatively sharp features, the isodensity contours, but they're limited by a few cells. And so, again, we're not, yeah.
We have 2 questions.
Sorry, yes.
Yeah, my question is exactly about numerical artifacts that you might have. About 2 decades ago, I believe in the mid-90s, Bruce Almagren did some simulations of star formation. Well, it was not at this level, of course, but he showed that the derived quantities such as the IMF depended on they were depending on the initial resolution, on the resolution of the grid. They were different, and this is because the density distribution is fractal, and you cannot simply use the grid of 1,000. Like if you use a grid of 512 or 1024 cube, at the low end you will always enter this regime where you've not sampled properly the structure.
Yeah.
How do you tackle this?
Well, so I'm limiting here to very high density regions within the shock structure, so only a few scalings. These are shocks that are something like Mach squared of the RMS Mach of the volume, so they're more than 25 times the background density. So these are extremely rare regions, and I'm only tracing down to about that density. So some of these are 200 times the mean density, going down to 25 times. As I showed from the initial simulation that you flew through, the structure gets phenomenally complex as you go to lower and lower densities, and it also changes its nature. It's no longer a collection of just shocks. There's actually some, more, what's the word I'm looking? A fluid with, with a curl rather than a compression. I can't remember for some reason because I'm dead from giving 2 talks today. But the structure in this volume filling fluid is much different. Yes.
So I'm wondering about the observational testability of these models in the following sense. In your model, if you take a beam,
Yes.
Presumably you can compute within that area
Yeah.
an average density
Uh-huh.
over all of these shocks with their different Mach numbers, their orientations, etc. There are a number of molecules readily detected in the radio whose intensity goes as the density.
Yeah.
So I'm just wondering, since you know the temperature well of these clouds, whether you can use such data to set constraints on whether this model is reasonable.
Yeah, I think so. We haven't done that here. This was basically a theoretical exercise to understand the structure. People have looked at the filaments in projection, and they've said, well, what is the profile of those filaments? And usually people find something that's close to Gaussian, but they're all limited by the beam resolution, more or less. So it would be nice to know if you're very aware of extremely high resolution, maybe I saw Mark sitting next to you, really high resolution radio data where you could actually trace out the structure, the internal structure of these filaments in molecular clouds and look for this in different lines. That would be great. Yeah, where you just take a bulk. Yeah. Yeah, because this reproduces the density PDF of the dense gas, my guess is that that won't be as informative as actually looking at the structure of individual shocks, but it's something that we can think about. Yes? Artistic? Vorticity. Well, no, actually it wasn't. I know what vorticity is. Yeah, of course, the fluid, I was thinking of doing a Kelvin solenoidal. Thanks, that's the word I was looking. Thank you. Yes, but anyway, yes, don't let that dissuade you from the rest of the talk, which I thought was amazing. So thank you very much for your time. Sorry for going over. Yeah. These are mine, so. Oh, the microphone is not mine. Sorry, just a second. Thanks.
I think it's coming. Yeah. Can everyone hear me? Yeah? Okay. So I'm Jerome Quintin, a senior PhD student at McGill University, and my PhD supervisor is Robert Brandenberger. So this will be a talk about primordial cosmology. So let me start with the current paradigm of cosmology, which is a lambda CDM model. It has 6 parameters, but if you focus on the primordial part, it's really the only last 2 that tell you something. AS is the amplitude of primordial scalar perturbations, and NS is the spectral index of its power spectrum. You could extend the model to include, for instance, the running of the spectral index, or the tensor to scalar ratio, which tells you about primordial gravitational waves, or non-Gaussianities, these FNL parameters. But all of those so far are either consistent with 0 or poorly constrained. The paradigm really, usually one adds inflation, and the reason is that usually a lot of inflation models will explain those numbers. But I want you to be aware that inflation is not the only possibility for the very early universe. To give a couple of examples, eperiodic cosmology, which is a contracting universe with an equation state P equals W rho with W much greater than 1, as well as stringless cosmology, which is a phase quasi-static filled with a gas of fundamental superstrings in thermal equilibrium, would give predictions in agreement with those numbers, as well as have new predictions that could be tested in the future, such as a tensor tilt that is positive. There are other scenarios as well, but I won't focus on that today. I just want to use that as motivation for looking for alternatives and have an open mind and try to test those alternatives. In particular, a lot of those are bouncing scenarios, meaning that the Big Bang singularity is actually replaced by a non-singular bounce, and before that, the universe was contracting. And my question today is, can we find generic predictions of a contracting universe? And to do so, we're going to take a very minimal assumption, which is to say, well, let's say we have matter in the contracting phase, which looks like the matter we have today. So possibly dust and radiation. And how do these fluids behave in a contracting universe? So they're described by an energy density rho and pressure P. They have a background, rho bar, P bar, and we add linear perturbations about that. The background equation state is characterized by the parameter W, and the perturbations are related through the sound speed when you have constant entropy. Note that from here on, the speed of light is set to 1. So the case of dust would be when W is equal to CS squared, and that's a very small number, and radiation would be the case where that's 1/3. From here on, I'm going to focus on the density contrast, which is the ratio delta rho over rho background. And the subscript K means that it's the Fourier transform, and K is the wave number of the fluctuations. This key scale here that will determine how the fluctuations behave is the gene scale, given by this expression, and its inverse is the gene's radius. So if you're on sub-gene scales, the pressure and the gravity really fight one another, and what you find is that you've got oscillations in your perturbations. Whereas if you're on super-gene scales, then gravity really wins over, and you've got gravitational instability, and your density contrast is going to grow as a function of time. And the question is then, if you're in a contracting universe, will this lead to black hole formation? First, let us understand a little better what are the scales at play here. So there's the Jeans radius that I already introduced, but there's also the Hubble radius, which you can think of as a horizon. And the difference is the sound speed. In the case of radiation, the sound speed is really of order 1, so these two scales are of the same order. If you make a sketch of time versus length scales, then the Hubble radius and Jeans radius lie almost on top of one another. And if you track a fluctuation with wavelength of order K inverse, then there's only two regimes. The sub-Jeans regime, where the fluctuations will be oscillating, and the super-Hubble regime, where the fluctuations will be frozen. They could grow in amplitude, but they won't collapse and form black holes because they're outside the horizon. That's not possible by causality. If you've got dust, then the sound speed is very small, and it would mean that the Jeans radius is much smaller than the Hubble radius in that case. Then there's a new regime that appears, which is the super-Jeans sub-Hubble regime. And in that regime, you'll get instability. The Jeans are gravitational instability, where the perturbations will grow, and they could indeed collapse and form black holes because you're still below the Hubble radius, in other words, below the horizon. So at this point, to solve the full linearized Einstein equations, one needs to specify some initial conditions. Examples could be a quantum vacuum in the asymptotic past, or a thermal state at some finite time in the past. Then we characterize the probability of forming black holes using the Press-Schechter formalism, which tells you that the probability of forming a black hole radius r at the time t is given by this Gaussian integral. And the key ingredients here are the critical density contrast, delta c, for forming a black hole, and sigma squared is the variance related through this integral over Fourier space of this density contrast through some window function. And then we say that the probability of forming a black hole is really high when the square root of the variance is greater than this critical density contrast. Let me show the results here in the case where one starts with a quantum vacuum in the infinite past. So these are color plots where the color is the probability of black hole formation. Red is very small, blue is a very high probability. The vertical axis is the radius of the black holes in units of the Hubble radius. And the horizontal axis is the Hubble parameter in absolute value. So you can think of it as a time axis, or if you will, the scale factor of the universe is getting smaller as you go to the right. So what we see here is that the first black holes that are going to form are the largest ones. So for instance, if you go over here, you see that at a value of h of 10 minus 9, you first form black holes, and it's the ones with the largest radius of the order of the Hubble radius. Also, the smaller the sound speed, the earlier this is going to happen. So on the left, you've got a sound speed of 10 minus 4, and on the right, 10 to minus 3. And this all makes sense with the analytic result, which goes as follows. The density contrast is inversely proportional to the sound speed to the power 5. So the smaller that is, the larger the density contrast. And also, the larger the Hubble parameter in absolute value, the larger the perturbations have become. One can give another example in the case where one starts with a thermal state at some finite time in the past. This is just an example, 10 to minus 16 Planck mass. And what we see is that a few orders of magnitudes afterwards, say around 10 minus 11, black holes will form. And the qualitative behavior is the same here. And in particular, as time progresses, more and more black holes could form with smaller and smaller radius. So the conclusion here is really that if you've got a long enough phase of dust-dominated contraction, then you're going to form black holes, and first Hubble-sized black holes, and that will happen well before Planckian densities are reached. In particular, the radius of the black holes will scale as 1 over the sound speed to a specific power. 5/2 is if you start with a quantum vacuum, or 18/5 if you start with a thermal state. And to give you an idea of what this means, let's put some numbers in. Say you've got a sound speed that is really, really small, something like 10 to minus 10. Then you get a radius for the black holes that is of the order of 10 minus 10 meters. And the corresponding mass would be like 10 minus 13 solar masses. And that lies in the range, the bottom range of primordial black holes. If instead the sound speed is still very small, but larger, say 10 to minus 5, then the radius is a lot smaller, something like 10 to the 12 Planck lengths. And the corresponding mass would be like 10 to the 7 grams. And those black holes would have evaporated by now, but it could still leave some imprints, like black hole remnants or gamma rays from the evaporation. Let me give you a couple of comments here. One notes that it's harder to form those black holes if the sound speed is, if it increases. In particular, we expect that to happen. If you've got a contracting universe, at some point, even if you start with dust, that will probably heat up and the sound speed will increase. On the other hand, it'll be easier to form black holes if you start with already some form of structure in the universe. Here, we really took minimal assumptions, such as a quantum vacuum or thermal state. So let me end with an outlook. This was really just a first estimate of black hole formation in the contracting universe, but we still found interesting results. In the future, of course, the analysis could be refined. And there's some interesting questions that we'd like to address. In particular, could the black holes pass through a bounce? At that point, I only talked about the contraction, but to observe them in the expanding universe, they would have to pass through and survive the transition from contraction to expansion. There are a few early studies that indicate that this could be possible. And if that's the case, then one could use observations to really constrain the bouncing models. Also, could there be specific gravitational wave signals? In particular, if the black holes merge in the contracting phase, that could be interesting to look at in the future. And more theoretically, I'm curious about whether the black holes could play a role in the bounce itself. For instance, if you've got those relatively small black holes that could lie at around the string scale, and perhaps string theory could tell us about something about what was the state of the early universe when it was really, really dense. So that'll be interesting. So that's it. Thank you for your attention.
Jerome, just a cautionary remark, because
Yes.
if one uses the pressure deformalism,
Yeah.
it's usually applicable to consider halos or let's say galaxies forming, but not the black holes if you do it after the Big Bang, because there is the angular momentum. So most of the mass that makes a galaxy does not end up in a black hole. You end up with a halo simply because there is some rotation. A little bit of rotation will prevent it going all the way to the Schwarzschild radius. And so you get the black holes make up 10 to the minus 4, 10 to the minus 5 of the mass in galaxies. And that is a pretty small factor.
Okay.
And so you need to incorporate that. It's also true for the contracting phase, that there would be some spin associated.
Yeah, that is assuming that there's no spin. Yeah. So the masses will be even smaller than the numbers I showed here. Yeah.
Ramesh?
Just a small point. You kept talking about dust.
Okay, yeah.
You mean dust in gravitational theory sense, or is it astronomical dust?
So gravity sense.
Okay, so what is your dust? Any pressureless gas?
Pretty much, or it could even be cold dark matter if you wanted. Yeah.
So it could be CDM.
It could be CDM, absolutely.
Right. But by the time you collapse, doesn't the radiation always overtake any CDM or other cold medium? Certainly during the Big Bang, radiation dominated for a long time, right?
Mm-hmm. Yeah.
Shouldn't that happen in reverse?
It depends. You don't necessarily match the amount of matter we have today in the contracting phase. It's not it's not symmetric necessarily. So there could be a lot more CDM in the past or radiation. We don't really know. So this is trying to be general here. Yeah.
Yes.
Does the black hole formation you studied so far back reactor give you some constraints on this bouncing model? The second question is how about exopology? Do they have this kind of issue?
Okay, so to answer the first question, definitely it could back react and it give you some constraint on the bouncing model. That was one of my last points here. So if at some point the universe is dominated by these black holes, then the picture really completely changes.
What type of bounce did you can this constraint so far?
So example, the matter bounce. By definition, the matter bounce is matter dominated for some period of time, so that would definitely apply. And you mentioned ecprotic. So black holes could form before an ecprotic phase of contraction, so you had matter followed by ecprotic. But in the ecprotic phase itself, because the universe is, the scale factor has a different evolution, it could wash out these black holes. So the energy density is growing a lot faster in ecprotic, so that the black holes could be diluted. Yeah.
Thank you very much, Jerome. That's it. And everyone is invited to step outside.